I'm Luca, and I'm going to present this solver that we realized together with Francesco Cavaliere and Daniele Levigo for the CVRP. If you're interested, you can also find our source code, the following link, but you can find the link also in our draft. So our idea is fairly simple, actually. So we just combined two existing algorithms, one for the CVRP, FILO in particular, and the other for the set partitioning, so a fairly straightforward strategy. And we devised so a control strategy on top of them. Let me explain a little bit what are these two algorithms. So first of all, FILO, which stands for Fast Iterative Local Search Localized Optimization, is an algorithm which I've published with Daniele some time ago, but that has seen a major revisiting together with Francesco. Its main components are an efficient local search engine, which explores several neighborhoods in a variable neighborhood descent fashion. In particular, we have cross-exchange variants. We also have inter and inter-route to-opt exchanges. We have an ejection chain and also a chain of to-opt exchanges, and also an intra-route link-Kernighan. Most of these neighborhoods, all but the link-Kernighan one, are explored by using acceleration and pruning techniques. In particular, we use static move descriptors as an acceleration technique to, let's say, perform some efficient evaluation of a neighborhood without re-exploring a portion of the neighborhood which cannot give us some improvement. And from the pruning point of view, we use granular neighborhoods to heuristically restrict the cardinality of our neighborhoods, and a technique that we call the selective vertex caching, which is a simple way to, let's say, perform a localized optimization of the solution instead of, say, considering the whole solution. This local search engine is then combined with a quite straightforward diversification approach based on simulated annealing criteria. FILO is combined with SPH, which is a set partitioning heuristic. It is based on the well-known CFT method for the set covering that was initially proposed by Caprara, Fischetti, and Toth. I won't give you too many details here, so I strongly invite you to follow the presentation of Francesco tomorrow, which will give you an in-depth description of it. So this is an high-level overview of FILO. It starts with a construction phase, which is based on a variation of the Clark and Wright, so fairly straightforward. But instead of, let's say, computing all possible savings, which are quadratic, we just compute a subset of them to make this phase linear, which I think, especially during this competition, can be it's a good idea, since the time to reach solutions is so important. We also may perform a route minimization. It is performed when we let's say estimate that the initial solution is using more routes than necessary. This is estimated by a greedy solution of the associated beam packing problem. And finally, let's say, main part of the algorithm, it is what we call the core optimization, where we actually employ all the components that I've mentioned before, the local search engine and diversification and so on. Both route minimization and core optimization are based on this abstract iterated local search procedure that you can see here. It's very simple. We basically first perform a shaking in a recreate fashion, and we destroy some localized portion of the solution. And then we try to optimize that area, and primarily that area, by using the local search engine. We then accept the neighbor solution with the simulated annealing criteria. And this process is repeated for a certain number of iterations or for a certain time limit. Let's see. Okay. This is the overview of SPH. It starts from a pool of routes, and it constructs a model, let's say an instance of the set partitioning. And then there are some steps which are inspired by the CFT. Particularly, we have a subgradient phase, which selects a set of, let's say, what we consider to be the most promising routes. and defines what we call a subinstance. This subinstance is then optimized by using a MIP solver. Some of these columns are fixed into the solution, and the process is repeated for a certain number of time, or for a certain for a certain number of iterations, or for a certain time limit. So this is how we combined FILO and SPH. So we kept the construction and the route minimization phases from the original algorithm, and then we attached a fast and a slow descent phases. Both of these phases share the same structure. That is what you can see here in the yellow box. We first perform a certain number of core optimization, a certain runs of core optimizations of FILO, and then we call SPH. And this whole process is repeated for a certain number of rounds. During its core optimization, FILO stores some routes into the pool, which is then used by SPH. So fairly, let's say, simple way of combining these two algorithms. Just let me say that the pool of route is never cleared, is never reset, so it's always increasing. But that's not a problem because of the subgradient phase, which selects a subinstance of the most promising routes. I'll briefly give you, let's say, the reasons for this kind of organization, some motivation, let's say. First of all, we have that FILO is executed several times, and this is done just to, let's say, reduce the likelihood of bad runs. Okay? Which, you know, if you perform one run, it's highly like that you end up in some local optimum, even though you have some diversification. And also because we want to match, this is of course related, the average quality results that we originally obtained with the original algorithm that was indeed run over several seeds and runs. We also have that every execution of FILO always starts from the initial solution. So you can think of it as a sort of multi-start approach with a little bit of memory, which is the pool of routes. We can do that because typically FILO takes, let's say, a short computing time to find reasonably good quality solutions for instances with up to, let's say, a few thousand customers. When we move to much larger instances, even FILO, because of its localized optimization, would take more time, more iterations. So as I'll show you later in the parameters tuning, for larger instances, we typically perform few iterations, but we allocate more time for every iteration. We also want to make sure that we are calling SPH when there is some space for improvement. So when we have collected enough new routes, then we call SPH, which is of course has some overhead, even though it's a fast algorithm. SPH is called for a short period of time, and we hope for the best. We hope to improve the solution actually. We found it to be especially, we don't really have, let's say, thorough statistics, but we experimentally found it to be especially effective on instances for which the solution require a lot of routes, and I think this is reasonable. Sorry. Then we have the two phases. You can think of the fast descent phase as a sort of fast intensification. Here we are trying to, let's say, reduce the primal integral as fast as possible. And this is done by performing short runs of FILO. Since we have fixed the simulated annealing initial and final temperature, if you are reducing the time, the effect is a faster descent, which of course it's quite likely to get stuck on local optima earlier because we are not diversifying enough. However, here our idea was that to perform this fast phase to reduce the primary integral at the beginning of the run as fast as possible and to gain some advantage with respect to the other competitors. Then there is this low descent phase that can be intended as a sort of diversification, polishing, but also final intensification, in which we just perform longer runs of FILO. So it's more likely that we obtain a better diversification and hopefully a better final solution. Now, as for the parameter tuning, both FILO and SPH have their own parameters, but I'm not discussing them here. Also, for FILO, we kept them as they were proposed for the original approach. We just changed the simulated annealing temperature in the slow descent phase, because we found that setting it to be 10 times smaller than what was proposed in the original approach worked better. For the SPH, the parameters were largely inspired by what is described in the paper, in the CFT paper. Now, as for the high-level strategy, we defined the parameters according to the instance size. In particular, we identified five classes from small to very large scale instances. And what we changed is the time allocated to the fast and slow descent phases, as well as the time and iterations allocated to rounds and runs, and the fraction of time allocated to FILO and SPH. We set these values, we define these values in a handcrafted way. We try to perform a little bit of local search around these values without too much success. Now, the idea that we follow is the following one, as I briefly mentioned before, that the larger the instance, the lower are the iterations allocated to rounds and runs, but the longer is the time for every iteration, because for larger instances, we cannot really restart too many times. Now, during the tuning, we optimized the average primary integral, and we eventually realized that that's, of course, not the best metric for the Formula 1 score. We should have optimized the Formula 1 score directly. That's because it doesn't really consider small instances which have a primary integral which is orders of magnitude smaller than that of larger or more complicated instances. Now, I guess I can conclude with the results. Very briefly, we obtained a fourth position over all the instances, and as you can see, at least we obtained the best average primary integral, so a result which is consistent with what we optimized for. On the X instances, we obtained a fifth position, so I guess we can hope for a similar result on the second phase. On the Belgium instances, we obtained a first position, and that's great, also because FILO was designed to be effective on larger instances. On classic dataset, we obtained again a fourth position, and here you can see the average and the median primary integral, which is not really comparable to that of 4 other instances. On the golden instances, again, we obtained a fourth position. And finally, on the LOGIORTEC instances, we obtained a second position. And this, I guess, it is because these are larger than most of the X instances, and thus I think FILO performed slightly better there on these larger instances, even though I don't even think that they have been derived from the same distribution of the X instances. And finally, I'm going to conclude with some contribution. We just devised a very simple iterative schema on top of 2 existing algorithms. The results actually show that this approach can be used to find some good quality solutions, especially for very large scale instances when we are given a very short computing time. And that's it.